Welcome back to the Deep Dive. Today we are packing our bags, virtually at least, and heading to a destination that, well, it usually tops the list for backpackers, digital nomads, and culture seekers. We are talking about Chiang Mai in northern Thailand.
It is a stunning place. I mean, you've got the misty mountains, the ancient temples, the incredible coffee culture. It feels very permanent, like it's been there forever and it'll be there forever.
Exactly. It has that timeless, serene vibe. It's the kind of place where you go to, slow down. But, and this is where our deep dive takes a turn, if you peel back the layers of that postcard image, there is a geological reality that city planners are genuinely losing sleep over.
It's the geology. Northern Thailand is actually the country's most seismically active region. You have active fault lines running right through the area. And the city of Chiang Mai itself, it's growing incredibly fast.
That is the tension we are exploring today. You have this rapid urbanization, hotels, condos, commercial centers just popping up everywhere, and it is potentially outpacing the safety assessments needed to keep them standing.
Right. And the core problem isn't just that earthquakes happen there, it's a blind spot in urban planning. Usually, when engineers look at risk in a developing city, they rely on generic global models.
So they look at a building and say, okay, that looks like a concrete building. Let's use the standard safety curve from, I don't know, California.
Or Japan, which is a bit like buying a suit off the rack without checking the size. I mean, it might cover you, but it doesn't really fit. Thailand has unique building styles, unique materials, and, unique construction habits. If you use a generic model from a different continent, you might be drastically underestimating or overestimating the risk.
So today we're walking through a fascinating piece of research that tries to tailor that suit specifically for Chiang Mai. We're looking at a paper titled Development of Seismic Fragility for Masonry-Infilled Buildings in Northern Thailand.
This comes from a team including Jirapat Wachuang and Panan Latcharote, representing institutions like the Asian Institute of Technology and Mahidol University.
And their mission, it sounds almost like sci-fi to me. They didn't just want to guess. They wanted to create a digital twin of the city's vulnerability. They wanted to move away from static census data, just counting roofs, and move toward dynamic, probabilistic physics.
They wanted to predict exactly how Chiang Mai breaks if the ground starts to shake. And to do that, they had to start with the building blocks, literally.
So let's build this digital twin. If we want to simulate the city, we first need to know what the city is made of. What is the body of Chiang Mai?
It is overwhelmingly one specific type. When the researchers did their surveys, they found that over 80% of the building stock falls into a category called reinforced concrete frames with masonry infill walls.
80%? That's massive. It's practically the whole city.
It is the defining structure. In the HAZUS classification system, which is the global gold standard for risk tools, these are known as C3 buildings.
C3. Okay, I want to double-click on that masonry infill part. To the untrained eye, like mine, that just looks like a wall. You have your concrete skeleton holding up the roof, and you fill in the gaps with bricks to separate the rooms.
That is exactly what it looks like. And historically, that is how they were treated.
Just room dividers.
Exactly. In simple engineering designs, those brick walls are often considered non-structural. You calculate the strength of the concrete frame, and you just assume the brick wall is dead weight. But in reality, during an earthquake, those walls play a huge, complicated role.
How so?
They add stiffness. A lot of it. Imagine a cardboard box. If it's empty, it's flimsy. You can crush it or twist it easily. But if you pack it tight with styrofoam, it becomes stiff. The brick walls are the styrofoam in the concrete box.
Stiffness sounds good when the ground is shaking, doesn't it? You don't want the building to wobble.
It is good until it isn't. And this is the nuance. Masonry is brittle. So, initially, the building is very stiff. It resists the shaking. But once the shaking hits a certain intensity, those brick walls crack and fail. Suddenly.
So the stiffness just vanishes.
Instantly. And when that happens, the building's behavior changes in a split second. The forces get dumped onto the concrete frame, which might not be ready for it. It creates a very complex, non-linear behavior.
So if you're a researcher trying to build a digital twin, you can't just ignore the walls in your math.
Absolutely not. If you pretend the frame is empty, you get the wrong answer. If you pretend the wall is indestructible, you get the wrong answer. You have to model that infill behavior perfectly.
And to do that, you need data. Real data. This is one of the parts of the study I really respected. They didn't just download a government spreadsheet and call it a day. They went full detective mode.
They really did. It was a multi-level survey operation. They started with field observations, literally walking the streets of Chiang Mai with clipboards and cameras. They used Google Street View to check facades and, double check their notes.
And I read they even used UAVs, drones.
Yes, they flew drones to get aerial imagery. This helps with things you can't see from the street, like roof lines, the spacing between buildings, and the depth of the structures.
But here's my question. Looking at the outside of a building, even with a drone, only tells you so much. You can't see inside the concrete. You don't know how much steel rebar is inside a column just by looking at the paint job.
That is the classic problem, and that is why they went a step further that most studies don't manage. They collected actual structural drawings, the blueprints, for hundreds of buildings in Chiang Mai.
So they could see the bones.
Exactly. They looked at span lengths, how far apart the columns are, they looked at column sizes, they looked at reinforcement details. This gave them a ground truth data set that generic models simply don't have.
So they have this mountain of data. They know there are over 100 representative buildings. But here's the problem. Chiang Mai has, 100,000 buildings? You can't simulate every single one of them individually, right?
Yeah.
That would take a supercomputer the size of the city itself.
It's computationally impossible, so they had to be smart. They face a classic data science challenge. How do you simplify without losing accuracy?
And this brings us to their sensitivity analysis. I found this result genuinely surprising. I think our listeners will too.
It is a great aha moment. So they took a baseline model of a typical Chiang Mai building, and they started tweaking variables one by one.
Like a control board.
Exactly. They turned up the concrete strength, then they turned it down. They changed the steel quality, they changed the shape of the rooms. They wanted to see which knobs actually move the needle on seismic performance.
Now, if you asked me to bet, I would assume the quality of the materials matters most. Like if you use cheap concrete, the building falls down. If you use high-grade steel, it stays up.
That is the intuitive guess. Most people think stronger materials equals safer building. But the math said something different. This study found that material strength, the compressive strength of the concrete and the yield strength of the steel, had a minor effect compared to something else.
There's the winner.
Geometry,
The shape.
the shape, and the layout. Specifically, 3 things. The number of stories, the span length, that distance between columns we mentioned, and crucially, the arrangement of those infill walls.
The arrangement, you mean where the walls are placed?
Yes. Think about a classic Southeast Asian shop house. You've seen them. The ground floor is a shop or a garage, so it has big glass windows or a wide-open rolling door. But the upstairs are apartments, so they have solid brick walls between the rooms.
We see those everywhere.
That configuration creates what engineers call a soft story.
Soft story.
The top is stiff because of the walls. The bottom is flexible because it's open. During an earthquake, the top part moves as one solid block, and all the stress concentrates on those skinny columns on the ground floor. It's like a bodybuilder standing on stilts.
That sounds precarious.
It is devastating. The studies show that these layout choices, having that open ground floor, mattered way more than whether the concrete was slightly stronger or weaker.
That is fascinating. It's not just what you build with, it is the shape of what you build.
Precisely. And because of this finding, they realized they didn't need to model 100,000 unique buildings. They could group them. They created 80 representative building models that captured those specific high-impact variations, like the open ground floor or the long span.
So those 80 models act as avatars for the whole city.
Exactly.
Okay, so they have their 80 avatars. Now comes the fun part. They need to shake them.
And this is where the sheer scale of the simulation gets wild. They selected 350 pairs of ground motion records. These aren't random. They're site-specific, tailored to the soil and fault lines of northern Thailand.
And they have to run these quakes against the 80 models.
Right, and not just once. They're doing probabilistic analysis. The total number of nonlinear simulations required was 224,000.
224,000 simulations. Now, I am not an engineer, but I know that nonlinear response history analysis, which is the gold standard method, is heavy. It's not something you run on an iPhone.
No, a full nonlinear analysis calculates the damage at every fraction of a second as the earthquake wave passes through. It tracks the cracking, the bending, the yielding. If you tried to run 224,000 of those on a standard computer, you'd be waiting years. It's the bottleneck of modern risk assessment.
But looking at the paper, they finished it in 2 hours on a standard desktop workstation. How? Did they buy a supercomputer?
No, they used a computational hack. Well, It is a sophisticated method, but it acts like a hack. It's called UMRHA.
UMRHA.
Oh, yeah.
Sounds like a monster. What does it stand for?
Uncoupled modal response history analysis.
Okay, let's unpack UMRHA. How does it cheat the system without cheating the results?
Think of a building shaking during an earthquake like a complex symphony. The building is twisting, swaying back and forth, and bobbing up and down all at the same time.
Chaos.
Total chaos. Analyzing that whole chaotic movement together is the heavy math. That is what takes forever. UMRHA breaks that symphony down into individual instrument tracks. These are the modes.
Okay, so it separates the swaying from the twisting.
Exactly. It says, let's look at just the swaying mode. Let's treat it as a simple pendulum. That is incredibly fast to calculate. Then it looks at the twisting mode as another simple pendulum. It solves these simple single degree of freedom systems one by one.
And then it just adds the tracks back together at the end.
It superimposes the results, but, and this is a critical detail in this paper, they didn't just add them up blindly. They accounted for coupling.
Coupling. Is that where the X and Y directions interact?
Yes. Real buildings in Chiang Mai are rarely perfectly symmetrical. They're irregular. So when the ground shakes in the X direction, left to right, the building doesn't just move left to right. It might twist. It might jerk forward in the Y direction.
Like if you push a shopping cart with a bad wheel, it veers to the side.
That is a perfect analogy. The researchers accounted for that bad wheel. Even though they separated the modes to do the math, they ensured the final result reflected that interaction.
So they got the speed of the simple method, 2 hours instead of years, but kept the realism of the complex interaction.
That's the innovation. They used parallel computing on an Intel Core i5 with 64 GBs of RAM. A nice computer, sure, but something you could buy at an electronics store, and crushed 224,000 analyses while they went out for lunch.
That changes the game for city planning, doesn't it? If you can do this cheaply and quickly, you can update your risk model every time the city changes.
Exactly. It makes the digital twin sustainable. It's not a one-time study, it is a tool.
So they've shaken the digital buildings. Now they need to measure the damage.
Yeah.
This brings us to the core concept of the paper, the fragility function. It sounds fragile, but it seems like a pretty robust tool. What exactly is a fragility function?
A fragility function isn't a crystal ball that says, this building will collapse on Tuesday. It's a probability curve. It answers the question, given this amount of ground shaking, what is the likelihood that the damage will exceed a certain level?
So it's managing uncertainty.
Everything in earthquakes is uncertain. The fragility function maps that uncertainty. You have an intensity measure on the bottom axis. In this study, they used peak ground acceleration, or PGA.
How hard the ground kicks.
Right, and on the vertical axis, you have the probability of damage.
And how do they define damage? Is it just looking for cracks?
They used a metric called IDR, or interstory drift ratio.
That sounds technical. Break that down for us.
It is actually quite visual. Imagine you are standing on the second floor of a building. IDR measures how much the ceiling shifts sideways relative to the floor you are standing on, like a shearing motion.
Exactly. If the ceiling shifts a few millimeters, your drywall cracks. That is slight damage. If it shifts a few centimeters, your columns might buckle. That is complete damage.
So they are measuring the drift. Now, I noticed they use a specific statistical method called MSA, multiple stripe analysis. The paper made a big deal about not using another method called IDA. Why the distinction? Are we just splitting hairs here?
No, this is crucial for the context of Thailand. The other method, IDA incremental dynamic analysis, involves taking an earthquake record and scaling it up and up and up until the building collapses in the simulation.
Like stress testing a bridge until it snaps.
Right, but here's the thing. Thailand has low to moderate seismicity. We aren't expecting the kind of megathrust earthquakes you get in Chile or Japan. If you scale a small Thai earthquake up by a factor of 20 just to make the building fall down in your computer model, you are creating a scenario that is physically impossible for the region.
You're testing for a ghost that doesn't exist. You're simulating a monster quake that geology says won't happen. Exactly. It is bad science for this specific region. So instead, they used MSA multiple stripe analysis. They picked specific stripes of intensity, but think of them as benchmarks. An earthquake likely to happen once in 43 years, once in 475 years, all the way up to the rare once in 5,000 years event. They analyzed the buildings at these realistic intervals to see what happened.
So it's grounded in the actual hazard of the region, not just abstract math.
Precisely. It keeps the probability real.
So after all the drones, the blueprints, the sensitivity analysis, and the computational hacks.
Hmm.
What did they actually find? What do the results look like?
They produced 18 distinct fragility functions. These are categorized by occupancy, commercial, residential, education, and by height.
So a city planner can look at a map, point to a three-story school, and pull up curve number 15 or whatever to see its risk profile.
Exactly. And the curves show a log normal cumulative distribution, which is just a fancy way of saying as the shaking gets harder, the chance of failure curves upward. But what stands out is the variation. Because they use those 80 representative models, you can clearly see how different a two-story house behaves compared to a four-story commercial building.
And this is where the gap comes in. We always have to ask, is this perfect?
And the honest scientist always answers, no, it's a model. These are analytical fragility functions. They are based on math and physics. The authors are very clear that for these to be perfect, they need to be validated against empirical data.
Meaning they need a real earthquake to happen so they can check if the buildings broke the way the computer said they would.
Unfortunately, yes. That is the only way to truly calibrate these models. There was also a specific technical limitation they mentioned regarding that UMRHA shortcut we talked about.
The music track splitter.
Right. It was great at predicting the peak drift, the maximum swing during the quake, but it struggled a bit with residual displacement at very high intensities.
Residual displacement being
Yeah.
how crooked the building is after the shaking stops.
Exactly. Did it snap back to vertical, or is it leaning like the Tower of Pisa? The simplified method had a harder time predicting that permanent lean for the massive events. But for the purpose of estimating immediate damage and loss, the peak drift is the most important metric, and the model nailed that.
So let's zoom out. We have this incredible framework. We started with a tourist walking down the street in Chiang Mai, totally unaware of the seismic risk. We ended with a sophisticated math model that predicts the future of 80% of the city's buildings. What is the big takeaway here? Why does this matter beyond the academic journals?
It matters because it bridges the gap. Before this, a city planner in Chiang Mai had to guess. They had to use a curve from the US and hope it applied. Now they have a tool that is built from the ground up using local data.
They can estimate losses, they can plan emergency response routes.
Exactly. They can say, if a magnitude 6 hits this fault line, we know that the commercial district with the open floor shop houses is going to suffer 60% heavy damage. That allows you to retrofit the right buildings before the disaster. It changes risk assessment from a vague anxiety into an actionable plan.
It empowers the city to protect its own future.
And the method, this combination of street surveys, representative modeling, and fast computation can be replicated. Other rapidly urbanizing cities in Southeast Asia and Vietnam in Indonesia could use this same playbook.
That is a hopeful note. It's using technology not just to build faster, but to build safer.
Absolutely.
Before we go, I want to leave our listeners with a thought that really stuck with me from this report. We often obsess over materials. We want the strongest concrete, the thickest steel. But this study showed that geometry, how far apart your columns are, whether you leave that ground floor open for a shop, often matters more than the material strength itself.
It really challenges our assumptions about what makes something strong.
It does. It makes you wonder, are we focusing too much on the quality of our ingredients when we should be focusing on the shape of the recipe?
That is the question.
Thanks for joining us on this deep dive into the engineering of Chiang Mai. Stay curious, stay safe, and we will catch you on the next one.